I know this is a Leetcode. To have a Leetcode hard question, right? Couples holding hands. Um, so we should probably release this on Valentine's Day, but it doesn't really matter. It's all about doing more practice questions so we can get a good job. Um, in one of these high firms. For example, you have Google asking this question, Amazon asking this question, and Facebook asking this question. And the question reads: there are N couples sitting in two N seats arranged in a row and want to hold hands. The people and seats are represented by the integer row, where row I is the ID of the person sitting in the ith chair. The couples are numbered in order. So the first couple being 0, 1, the second couple being 2, 3, and so on, with the last couple being what 2n minus 2 and 2n minus 1. So return the minimum number of swaps so that every couple will be sitting side by side. Um, a swap consists of any two people. Um, a swap consists of choosing any two people, and then they stand up and switch seats. Cool. So this is a very interesting problem. Uh, Very hard to get, I would say, unless you've done like certain graph theory problems, or you've probably even seen what's it called, a few other graph problems. But I wanted to hit the hint and see what they'll give us. Right? The hint says that say there are two seat couches, right? For each couple, draw an edge from couch of one partner to the couch of another. Right. So basically, the hint is very helpful. It says draw an edge. Right, so it's giving you the idea that this could be a graph question. I can see how you know um you could think it will be another way. Initially, when I think I had a problem. I think it was like a dynamic programming question. I was like, oh, but the hint is very helpful, right? It's very helpful to think about each couple as being in a group, right? And then we are able to link those groups. So once we link every group, then we'll be able to find the number of swaps that we need, right? So basically, we want to go through our row with two numbers at a time, right? So we go two at a time and then the next two and so on and so forth. Now, if we check and those two are in the same group, right? Then we're in a good space, right? We don't need to make any swaps. But if they are not in the same group, right, then we need to at least note that, and in the end, with that, we'll be able to find the number of people to swap. So, looking at first example, right, you want to swap between 2 and 1, right? Swap those two people. So, I had to be 0, 1 and 1, 3. And then for here, we have 2, 3, right? They are next to each other, and 1, 3. Sorry, 0, 1, who is also next to each other. So, that is a good thing on that front. And that is why we have 0, right? We do not need to make any swaps because everyone is beside each other. But without further ado, let's go on to the drawing board so I can like explain how we're going to solve this problem. We're going to use the unifying method, right? And I want you guys to think of this in terms of graphing. So let's continue, right? So for the first question, for the first group we had numbers 0, right, 2, 1, and 3, right? This was a group, or this was the rows. And as you guys can see, we want to just swap these guys. So once we make this one swap, we are fine. Now the problem is that we could probably view these guys in terms of their groups or in terms of their nodes, right? So basically, we'll say 0 and 1, they should be in one group, right? And then we would have 2, right? 2 and 3 also in another group. So I want to call this group A and this group B, basically, right? Now, what we want to do is that we take two elements at the same time and see if they are in the same group. If they are not, then like whether they are or they are not, we are going to connect to them, right? So we have first we have 0 and 2, right? Are they in the same group? Zero is in group A, two is in group B, right? So I'm going to connect them. So um, basically, let me try and draw notes like this, right? We are connecting them. So we are saying we are moving from an A, right, to a B element. And then we move to the next one and say, okay, now we've already made this union. And the next one also tries on the same union, right? So the same union, because it's going to be one, right, connected to three. And mind you, B is in group B, A is in group A. So overall, we have just one connected component, right, which is A and B. When we do our union find, we'd have like just one parent, so we have just one connected component. But i- one connected component kind of means that there are two elements that are at least in it, there are elements that are connected the way we want, right? So the formula to get the number of swaps we need is what the vertices, the number of vertices, right? So NV minus the number of connected components, so NC basically, right? This is kind of what you want to have, right? NV minus NC, that's the formula. That'll tell you the number of swaps you need. And I think this follows graph theory, and I liked one of the people's explanations, and I think we'll go through that because that's what was helpful for me to understand what we're doing. But let's go for a bigger example, right? In terms of so let's say we have 0, we have 2, we have 3, we have 4, we have 5, 1, 6, 8, 7, and 9. Right now, with this, we initially can see some elements are next to each other, right? Like correctly. So I'll say, let's put them in groups. I will say like 0 and 1 are in the same group. So I'll call it group A, or the one group, the 0th group actually. Let me see, 0th. And then same for 2 and 3, like so group B. For 4 and 5, group C. For 6 and 7, group D. And for 8 and 9, right? 8 and 9 are in the eighth group, or the fourth group, I'll say. So second, actually FST first, right? Third, and then fourth. Now, what we want to do is to find like group. We want to group people, right? And if any group is redundant, right? Like for example, we have in our previous example where we had an A and B, right? With our union find wouldn't like be a problem. We're just going to do have just like essentially in the end one connected component. It's going to tell us the number of connected components we have, right? So we just have one connected component in this case. But let's look at this one. So here we have 0 and 2. These are our first two. And you see here we are combining something in A, right, towards something in B, or the 0th group, right? So we have this connection between these two groups. And now let's go 3, 4. 3, 4 actually has what? An element in the B group connected to what? An element in the second group, right? Or in the C group. So we have B connecting to C here. And then we form a cycle because we find out that with 5 and 1, 5 is in the second group, and 1 is in the first group. So we have a connected component here, right? A complete component here, right? We have A, B, C. It closes as one cycle. One element is here. And you find out that we, it really follows through because we have elements that are next to each other. Like we have 3 and 4. Oh, sorry. We have 2 and 3 who are next to each other. Like even though the permutation is there based wrong, because like we want in groups of two, right? And then we have 4 and 5, and then we have what, one here in the end and 0 here. So basically, with our number of swaps, right, we want to make sure that we had one next to the 0, and then move these guys like accordingly. That's how like you ideally see it, right? Now, I'll show you guys how you optimize only do it, but like with the union find, basically you're going to use union find, and then you connect these three components. So in the end, you have three components here, and now let's continue from here. So we have 6 and 8, right, which is what group D connected to group E, right? And then 7 and 9 is also the same thing. So you have a D connected to an E. Again, basically just the same thing. So in the end, you see we have like two complete components, right? Or two connected components. You have components here and this component here. Now, as I showed you, the formula is saying what's n v minus nc. So we have those are the n, right? The number of vertices is what all the number of points we have divided by 2, right? Which is n. So here is 5, and then we have two connected components. We have what this and this. So we have in the end the number of swaps we want to make is 3, right? And if you were doing it ideally, right? Let's say you had if you do it by hand, you see that the best way you can do it and say 2, and I'm trying to rewrite it the whole thing. So 5, 1, 6, 8, 7, and 9, right? Now, what you want to do is initially you want to swap 1 with 3. I just want to prove that it's actually 3. I want to prove that now this number of swaps I want to do is 3. So you swap 1 with 2 here, right? And then you swap 8 and 7. And then you swap so let's say with the first two swaps, I want to rewrite this. We have 0, 1, right? These are connected. They are supposed to be the way they are, right? And then we have 3 and 4, right? And this is a couple. Hold on. Sorry, 3 and 4, not a couple yet. How do I reverse this? So so then I'm just rewriting, right? And then we have 3, 4, right? And then we have 5 and 2. And then we swap 8 for 9 for 7. So we have what 6, 7, 8, and 9. So the couples being next to each other, I have 6 and 7, right? They belong to group D, and then 8 and 9, they belong to us, group E. Here, right? So now this is what's left. And we've made what one swap here and another one here. Now the last swap we'll need to make is what 2 and 4. We swap them together. Now once you swap them together, I have what 0, 1, right? It's connected already. And then we'll have 3, but next to 3 will be 2. As we have here, we have it with a B, right? And then we'll have what excuse me. How, what? Oh no. It looks bad. Guys, but I think I was pressing it too long. Yeah. So 3 and 2 next to each other, and then 4 and actually sorry 5 first, and then 4 next to each other. And then we have 6, 7 next to each other, and 8 and 9 next to themselves. So then this is how you do it. So basically, I just wanted to prove that you do it in 3 swaps, right? And then the formula is the number of vertices minus the number of complete components. So without further ado, I want to go into the code, and I'll just briefly read through someone's explanation online. Thank you. So first we will need the union find class, right? And then we do the parents as I said. So public class union find, and then what we need is our parent, and we need a rank. And if you have no idea of how to write the union class find, you should probably do like some research on how to do that, or you wouldn't even understand how I'm doing this. So public class union find, and when you call union find, I want to give it an n, right? The number of components, and then once the parents equal to new int, um, uh, so we have n. So basically, we have 2n, right? And yeah, 2n, and then parent, sorry, and then the rank element is also what, 2n. Am I missing something? Yeah, I think I'm missing something. So basically, it's not 2n. I want it to be n, basically, right? N, where n is the number of groups, right? So we'll be doing it for each group, actually. So instead of the eighth group or the bth group or something like that, right? We want to do it in terms of numbers. So we'll have the 0th group, the 1th group, and so on and so forth. So initially, we have 5 groups with the example that I recently just showed you guys, right? And then I want to call component and set it to n. And then for in case equal to 0 and case less than n, right? Standard find basically. And say the parent k is equal to k, and then we set each um groups rank to what, 1, and public class. So we want to have find parents, so I will use that later on, right? So so while the I is not equal to all the parent I, right, then we want to do path compression. Standard find, guys. Standard find. Path I, and then we test the I to all the parent I. And when that terminates, we return I. And then now public and make this a void method today. It's a union and it's union J, right? So and let me call it P1. P1 is find parent of I, right? And then P2 is what find parent of J. Now, if the both parents are equal, right, then it's already connected. So we want to return. If not, then if the rank, actually, rank of P1 is greater, come on, is greater than the rank of P2, then we want to then increase the rank of P1 in this first, right? So we add that rank of P2, and then we'll set the parent of P2 to P1, right? And then we'll do the opposite if the other case is that, so rank P2 plus equal to the rank of P1, and then parent P1 is equal to P2. So once we are done connecting components, right, we want to reduce the number of components we have. So we say this, and then we return here, basically. And then I want one final class to return a number of components. Now to call it count, actually. I guess we return components. Right, so it returns components here. So that's that. And basically, like I wanted to what we were doing initially, right, with the parents. So first we want to call the unifying method, um create our own unified object, right? Call it n, and actually let's get n first because it's not provided. So int n is what the row dot length divided by the 2. So for the first example, for example, we have like 4 elements, so we have 2 groups, right? And now call our union find, and then basically now I want to loop through the row, right? So k0 and k is less than n and k plus plus. We are looping through the row, and we want every 2 elements together. So this and this. So the first one I'll call it int I. Int I is equal to row, and the way we get this is by saying row 2 times k. So initially it is k of 0, right? So it will going to get it's a row of zero, and row of zero is going to be the first element, which is R0, right? And then its next element is what? 2 times k plus 1. So depending on whatever the key is, right, it would be going through windows of size 2, and we go. So I'll say int j is equal to row 2 times k plus 1. Now to get a group of um, group I, right, if you want to get a group of I, basically we divide whatever number we have by 2, right? So, like for example, how do we know three's group? Three would be in the what? Um, in the group 1, right? Because we have 0 and 1 all in the first group, so that'll be in the 0th group, and then 2 and 3 in the second group. But how did I get? Sorry, in the second group, which is the ith group, the first. Sorry, first group, I guess, because we are starting from 0, and now so the second group is the first group. Anyways, right. So how did I know that this is in group 1, for example? Basically, we get it to know its group by dividing it by 2, right? So say I divided by 2, and then group the group of J is J divided by 2, right? So basically, we want to union the groups. That's what we wanted to do, right? So that's what we're doing in our previous examples, right? So you say union of a union of group I and then group J, right? So basically, this is what we do. In the end, we'll get the number of connected components, right? So for every fresh union, we are going to um, subtract the components by what 1. That's going to show us the number of, in the end, the components is going to give us what the number of connected components we have. And then we want to use our formula, which is basically the number of vertices, right? Which is n, right? We have n vertices minus the union find of our count, right? Our count is the number of connected components we have here. So um with that, I hope it works and you guys could understand the question. So passes to test, and we pass everything 100%. Great, great. So this is a solution I was looking at. I was looking at this person. I think it's called Jo Jolion one. Okay, Jolion 129. She goes through the graph permutation and graph decomposition, right? Like connecting the components and so on and so forth. So this would be an interesting thing to read. You can also look at my solution. I'll probably post it up, and this is basically what I'll do, right? So we have these groups. I have zero to basically share the same row, right? That's what I copied, and then she connects them. So you see, these form a cycle, right? So it's one complete component. This also form a cycle, one complete component. So you have two complete components. So in the end, if you have two complete components, right, and then our n is 5, then it means the number of swaps you have to make. And I prove that it is 3 swaps you have to make. Then that like 3 is the least you can make. Then that will give you the least number of swaps you have to make. Um, so I liked her solution also. I think it's she used, is it DFS? I think yeah, DFS. I might be wrong. But basically her explanation is very helpful. I hope mine was also as helpful. If not, leave some feedback. Let me know what you feel, so I can improve that on my next videos. But I really liked making this video. And I'll catch you guys in the next one. See ya.